quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Thank you very much for this very kind introduction, even with citations in French. I am deeply honored to have been invited to give this Dirac lecture and to receive the Dirac medal. You know, Paul Dirac was, since I started learning quantum physics a long time ago, he was one of my scientific heroes. His theoretical work is extraordinarily deep, and it is motivated by pure curiosity. So it's a perfect example of blue sky research, the kind of research I would like to talk about to you today. In fact, with some other great scientists, people like Einstein, Bohr, Schrödinger, Heisenberg, de Broglie, whom I will be talking about too, he changed our view of the world, not only at the microscopic scale, but also at the macroscopic scale of the whole universe, because quantum physics and relativity are important to understand the world. And this understanding of the world is motivated only by curiosity. There is no reason when they started this research, they were not looking for some utilitarian application, and this is what blue sky research is about. So I will be talking to you about the beauty of blue sky research. I hope I will give you a feeling about it, about its necessity too, and you mentioned the fact that it becomes difficult to get funding for this kind of research. And I think one of the reasons the funding should come is that, in spite of the fact that it is not aimed at specific application, very often in serendipitous ways, blue sky research has led to innovations which have changed our lives, and I will talk about that a little bit today. Of course, the search for understanding nature and man has started a long time ago. Questions about nature and about the place of man in the universe have first been addressed, of course, during the history by religion, by mythological stories, even by philosophy. But the question has been addressed by science only a few centuries ago, and one might say that the story started during the Renaissance, when objective observation of the world followed by rational thinking gave rise to modern science. And blue sky research is about this modern science. I think one way to start this talk would be for me to say to you a few words about the institution I belong to. I will not be talking about the École Normale Supérieure, but about the other one, the Collège de France. The Collège de France was founded, in fact, during the Renaissance in 1530 by the King Francis I, who had been waging long wars in Italy, but from Italy he brought back not the warrior spirit, but the spirit of the Renaissance. And when he, in 1530, he decided to found what was then called the Collège Royal. The idea was to gather scholars who were teaching, giving public lectures on all kinds of topics which were not taught in the medieval Sorbonne. The first topic was mathematics, and also languages spoken in the Middle East, like Hebrew and Arabic, which were not taught in the Sorbonne. And then things have expanded. All fields of knowledge have been taught in this Collège de France, which has survived all revolution upheavals, and which is now called the Collège Royal, became in the 19th century the Collège de France, and this is the building in which it is located today. There are about 50 professors who are specialized in all fields, in exact science and humanities as well. And I think the spirit is blue sky research in the sense that the research is free. They follow their line of research as they want. They just have to change their lectures every year. And this is, I think, blue sky research in the true sense of the word. A few luminaries in Collège de France have been Champollion, who deciphered the hieroglyphs in the 19th century. I know that the British think it's Thomas Young who did that, but the French says it's Champollion. And Ampère, who discovered the laws of electricity and their connection with magnetism. Claude Bernard, who was the first who started experimental medicine. And Henri Bergson was a philosopher. So you see it spans a wide range of fields. And this knowledge, the important point, and I think you have it here also on at the bottom of this poster about New South Wales, mixes humanities and science. And it is very important, because if you want to do science, you have to have an open mind, and you have to have a mind open to free thinking, and this is something that you get from humanities. And in order to show the connection with that, I will start talking about blue sky research and how it probes the universe and the place of man in it. That is, science for the universe, and the place of man is humanities. And I show here two different pictures. On the left, you see a clay tablet on which strange signs have been written by a scrivener about 4,000 years ago. And for the common man, it makes no sense. For the layman, you cannot make any sense of it. And on the right, you see in false colors the intensity fluctuations of the cosmological background of the universe, which has been detected by satellites orbiting the Earth. And again, for the layman, it makes no sense. Now, the research means that you take information which makes no sense unless you have a theory or unless you have a model. And from your knowledge, you can make sense out of it. You can relate it to a context and build theories or build models which teach you think beyond the mere aspect of these things. For example, in the left, a specialist in Assyriology will be able to tell you whether this message is a piece of, is a contract or a list of furnitures for the king's army or something like that. And from thousands of tablets of this kind, a civilization which lived 4,000 years ago revives, and you learn about it. And on the right, from these fluctuations, cosmologists will tell you that it tells you what happened 14 billion years ago when the universe was very young. These fluctuations, which are of quantum origin, gave rise to the start of the stars and the galaxies, and you understand what happens in the universe. So you see, it might sound a little bit artificial, but you see that blue sky research is in all fields, and it means that you have first to collect data, but collecting data is not enough. You have to make sense of the data you collect. You know that Lord Kelvin said at the beginning of the 20th century that beyond physics, it's only collecting stamps. And by that, it means that collecting data and just making collections is not science. To do science, you have to connect the data that you have obtained through a theory and in order to predict new things. And this is what blue sky research is about. And a lot of money is spent on blue sky research. I will give you here a few examples. These are telescopes on top of an Hawaiian mountain which are probing the depths of the universe. Here you see one of the detectors at CERN, a huge cavern underground which detect the results of collisions between particles, and which was used, for instance, to discover the Higgs boson 2 years ago. Here you see the Planck satellite before it was launched, and this satellite is one of the satellites who mapped the cosmological background because it was carrying a lot of radio frequency detectors. And here you see these two buildings at right angle, kilometer-long buildings which house laser beams which measure the distances between two mirrors on the two arms. The idea is that tiny changes in this mirror lens will allow us to detect gravitational waves coming from the collapse of stars, from explosion of supernovae, and so on. So this is really blue sky research in the true sense, because we are looking at the sky and trying to get information about what's going on. And you know, when you look at these huge realizations which have involved thousands of workers and technicians and engineers. The scale reminds us of what happens during the Egyptian time. It's pharaonic in dimension. And in the Egyptian times, the pyramids and the temples were built in order to make sense of the place of man in the universe too, but it was through religion. Here it's through science, and we learn where we are in the universe through these kind of experiments. This started long ago with Copernicus and Galileo. We learned that the Earth was not at the center of the universe, and it was rotating around the sun. And in the 20th century, we learned that the sun is only a small, at the peripheral part of our galaxy, and that there are billions of other galaxies around. And this is what we learned from this kind of experiments. You see here a famous picture from the Eagle Nebula taken by the Hubble telescope, and it looks like clouds, and these are gigantic clouds which are light years in dimensions. Inside these clouds, stars are continuously forming, so we learn that the universe is not static, it's in perpetual evolution and formation. And we also learned something new during the last 20 years. Most stars, maybe all stars, have planets going around them, and these planets are now detected. Thousands of these planets have been detected. One way to detect them is just to look at the tiny change of the light of the star during a partial eclipse, when the planet is between the star and the observer. There's a very slight change in the luminosity of the star, which is very difficult to detect, but with the improvement in astronomical observation, it's possible to do that. And some of these planets are within the distance range which makes them inhabitable. So very probably we learn soon that there is life in other parts of the universe, maybe intelligent life. But this is blue sky research because we will never be able to get there. These are at millions of light years or thousands of light years, and physics tells us that it's impossible to get there. So does it mean that it's not important to know? It's certainly important to know because it gives us a feeling, it tells us our place in the universe, and we learn that our place becomes smaller and smaller and smaller, and paradoxically, we become greater and greater and greater from this knowledge because we know more and more about the world around us. So this is the first part of the first aspect of blue sky research I wanted to talk about. Now, it's difficult as a physicist to talk about blue sky research without talking about theory and the connection between theory and experiments. All the great physicists which have succeeded one another since the 17th century, Galileo, Newton, Maxwell, Einstein, Schrödinger, have given, or Dirac, have discovered an equation which describes some part of the natural world. And this equation describes in mathematical terms the beauty of the world because it describes some kind of symmetry in the world around us. And this gives a lot of predictive power and beauty to the theoretical equation. Of course, it's very hard to give a feeling about the aesthetics of an equation to someone who is not a mathematician, but I'll try at least to give a feeling about that. And the first equation I will start with is, of course, the only one that everybody knows. It's the most famous equation, and you see, with only 5 symbols, it describes a lot of things. It tells us that any speck of matter, however small it is, contains energy, and energy is related to the mass. And because the speed of light is so big, you have a huge amount of energy within matter. And if during a reaction, chemical reaction or nuclear reaction, the final states have a different mass than the initial states, the mass difference is transformed into energy. If this energy is released quickly, you get the atomic bomb, or more precisely, the nuclear bomb. But if it is released in a continuous way, you get nuclear power plants, or you get the energy released by the stars. It's transformed into light, and the light transports the energy to the Earth, and this is how we can live here. Until the 20th century, this was a mystery. Nobody knew how long the stars will be able to radiate, because nobody knew what was the origin of this radiation. But as always in physics, or very often in physics, when we look at an equation, you ask other questions, and it starts to become complicated, or more complicated. For instance, I told that light has energy, carries the energy from the sun to the Earth, but we also know that light has no mass. So how come you can have energy without mass if you have E = mc²? And the explanation comes from the fact that the real equation is a little bit more complicated. In fact, what I wrote, the equation I wrote was the equation relating to a motionless object, and m was the rest mass. Now, if the object is moving, you have a more complicated relation involving the mass, the energy, and the momentum of the object, the momentum being classically the mass multiplied by the velocity. So you have this equation, E squared is equal to P squared C squared plus M squared C to the fourth. And if P is equal to 0, you recover the simple, well-known formula, E equal MC squared. But if M is equal to 0, then you just get E equal PC. And this is a formula which holds for light. Light has no mass, but it has, of course, it cannot be restless. It moves at the velocity of light, and it carries momentum related to its energy. And this momentum plays a very important role. When light is absorbed by a medium, the momentum gives a kick, and you have what is called the radiation pressure force. And this force has been used recently to slow down atoms and to trap atoms. So you see here a cloud of atoms which are produced, very slow atoms, very cold atoms, which are slowed down by this radiation pressure force at the intersection of 3 laser beams. But here I am anticipating a little bit, just to show that a very simple equation holds a lot of physics which was not put in the equation in the first place. In fact, this equation, and I'm afraid that the bottom line is missing, but I think we can make out what I was writing here. I go back to this equation, and I think this equation is very simple, and it's simple in 2 different meanings of the word. It's simple, of course, because even a schoolboy can understand what it means. And it's simple also because it expresses a very simple property of nature, the invariance of physical laws under translation at constant velocity. This is called Galilean invariance, and we all experienced it. If you are in a car or in a train which is moving at a constant velocity, and if you don't look through the window, you don't know whether you move or not. And if you look through the window and you see a passing train, you don't know whether you are moving or it's the other train moving in the opposite direction. Galileo had understood that, and this is called Galilean invariance for mechanics, for the motions. And the genius of Einstein was to extend this to all kinds of physics, and he extended to the laws which are ruling light, electromagnetic laws. And by just doing that, with a few steps, he came to this equation, which apparently has nothing to do with the motion and invariance, but this equation stems from that. And with another few steps, he arrived to other equations that I don't want to write here, which showed that time does not evolve at the same speed for clocks which are moving past each other with constant relative velocity. This is called time dilation, and this is a very important step. Up to that, the physics of Newton was assuming that positions depend upon the observer. If you change position, you will see objects under different angles. Their position will change, but it was assumed that the time was a universal parameter. Einstein showed that time is changing with position. And in fact, there is, a concept of space-time. Time and space are intermingled, and you have equations which describe how they change when you make a transformation. This is called spatial relativity, and it has, of course, tremendous consequences. But Einstein went one step further when he tried to put gravitation into the picture. And again, we know from Newton's law that gravitation is a force which is exerted between bodies. But Einstein tried to understand deeper what it meant, and again, it went back to Galileo. Galileo had found out that different masses fall in the gravitational field at the same speed. And this was not obvious at all. Since Aristotle, it was commonly assumed that heavy bodies would fall faster than light bodies. And it is assumed that Galileo made the experiment on the Pisa Tower, the Leaning Tower, by just letting 2 different weights fall, and that he found that they fall at the same speed. Apparently, he never did the experiment, because if he had done the experiment, he would have found Aristotle's result because of the air drag. In fact, he did just a thought experiment. And this thought experiment is described in in a kind of disputation he wrote between two people. One guy was taking Aristotle's point of view, and the other guy, Galileo's point of view. And Galileo said, okay, I take your point of view. We assume that the heavier body falls faster than the lighter one. So now assume that I just link the two bodies together. So according to Aristotle, they will find at some intermediate speed, because the light body will be like a parachute for the heavy one. But taking the argument on the other side, the total body is heavier than the heavier body, so it should fall faster. So we have a contradiction, and the only way out of this contradiction is to assume that they fall at the same speed. This was blue sky research again. And then Newton came, and he gave an explanation to that. He said, okay, this means that mass has two meanings. The mass is the quantity which describes how strongly things pull towards each other. This is the gravitational mass. And mass is also the inertial mass, the resistance to the change of motion. And if you assume that these two masses are equal, then the two effects cancel each other. If you increase the mass, the force will be bigger, but the resistance to the motion will be bigger, and the motion will be the same for all masses. And then Einstein made another step further. He found out that this means that you cannot make the difference, again, the relativity argument, you cannot make the difference between the pull, the gravitational pull, or the kind of pull you feel if you are in an accelerated body. For example, if you are in an elevator, you are not able to tell whether your body is pressed to the ground because of gravitation or because it is pressed to the ground because the accelerator is moving forward. And from that, with a few equations, he came to general relativity, which can be stated very simply. You have matter and energy on one side, E equal mc squared, which tell to space-time how to bend, and a mass which is in space acts a little bit like putting a mass on a rubber sheet, changing which curves the space around it. And this curved space tell to matter energy how to move. Straight lines become curved lines, and the particles or the energy, which is light, is going around this curved space line. So this is general relativity. And again, it comes to a very simple consideration, and it has tremendous consequences going beyond this consideration. For instance, Einstein found out that the light beam grazing the sun should be deflected because it's a mass which is going into this perturbed space-time. He computed the angle of deflection, and this was observed during a famous solar eclipse by Eddington in 1919. The apparent direction of the star was slightly modified during the eclipse because the light beams were grazing the sun surface, and the angle found by Eddington after small corrections was exactly given by the general theory of relativity, and this was a triumph of theory. And also, in the same theory shows that not only the space is bent by gravitational field, but time is changed too, and the time given by a clock depends upon the age in the gravitational field, and this was also verified later on by experiment. But in 1919, when this experiment was done, Einstein became overnight famous. It was the end of the First World War, and the German physicists were ostracized by the French and the English, but the discovery was so huge that Einstein was able to overcome that. And I come back to Collège de France. You see here a picture of Einstein welcomed by Langevin, who was a professor at Collège de France in 1922. And you see here the big crowd. It is the same building I showed you before. The crowd which was trying to get inside the building for Einstein's conference. You see, it's dated by the fact that there are only men in this crowd, and they all wear hats. And I don't see any hat here around. So things have changed. But you see, this is the beginning of the fame of scientists and physicists. And you see at the bottom Einstein lecturing in the lecture hall about general relativity. And I think almost nobody understood what he was talking about. In fact, when I started my physics courses in Paris just before entering into this École Normale, which is superior at the same time, I was in a preparatory school, and we had an old mathematics professor this professor had been through First World War, so he was very old in the 1960s, and he told us that he attended this conference. So he must have been one of these guys with a hat, and he told us very honestly that he did not understand a word of what Einstein was talking about. So you see, it's very counterintuitive, time depending on clocks, which give different times with different speeds and so on. And this is what you said about the hidden beauty of physics. You don't see with your eyes, but you understand and you see through deduction, through reasoning. Another part of the story, which is even more fascinating, has to do with quantum physics, and again, Einstein is involved. So I come back a few years earlier. Einstein, at that time, was trying to understand two puzzles at the same time, and very simple puzzles. When you hit a body, the body glows some light. We all know that. And at that time, it was possible to find the spectrum of the light, which was grown by the body, because detectors, infrared, UV, and visible detectors had been developed, so you could measure the spectrum. And by measuring the spectrum, one found that for each temperature, there was a maximum. It was a kind of bell-shaped curve. And bell-shaped curves are ubiquitous in physics, but classical physics did not give a bell-shaped curve. It gave a curve which increased energy when you decrease the wavelengths, and it was called the UV catastrophe. Nobody understood that. And Lord Kelvin said, this is a small problem we still have, but if we can solve it, we have solved everything. And another issue which was not understood is the photoelectric effect, which was also measured at that time. The fact that metals irradiated by light emit electrons, and the properties of this electron could not be understood with classical physics. And the genius of Einstein was to strike two birds with the same stone. He solved the two problems by assuming that light, which was up to then assumed to be a wave, was also made of discrete lumps, particles, quantum of light, later on called photons. And these photons have an energy which is proportional to the frequency of the light, the proportionality constant being Planck's constant. And the equation is not really visible at the bottom, but the fact that energy and momentum is related shows that each photon carries a momentum which is h nu over c, that is h over lambda. And so the shorter the wavelength, the bigger the momentum of the photon. And this looked simple. It's explained. You know, again, Einstein made reason through an analogy. He said, we know another bell-shaped curve. The distribution of atomic velocities in a gas, it's called Boltzmann law, is well known. Boltzmann assumed that the gas was made of particles called atoms, and it was an assumption because nobody had seen that atom was just an hypothesis. But if you assume that and just use the laws of thermodynamics, you find that there is a maximum velocity. For example, in this room, the maximum velocity for oxygen or nitrogen molecule is something like 400 or 500 meters per second, and you have less molecules going faster and less molecules going slower. And Einstein said, if I assume now that light also is made of particles, I will find a bell-shaped curve for the black body radiation. And this is the way he introduced the photon, just by making an analogy with Boltzmann. But this was a big step, because it merged two concepts which in classical physics does not make sense. A particle is well localized, a wave is delocalized. How can a wave be a particle? This was a big question. And this question is, becomes very, very directly observable if you look at the Young double slit experiment, which was a famous experiment done by Young, who was the competitor of Champollion for deciphering the hieroglyph, but I think was a better physicist than an Egyptologist. And he did the experiment with a source emitting light with a screen having two holes. And then you look at the light distribution on the second screen, and you see that you have maxima and minima, you have fringes. And classically, it's explained very easily by the fact that in some directions, the two wavelets add their amplitude because they are in phase. And in other direction, one wavelet is maximum while the other one is at a minimum, and they cancel themselves. So if you assume that light is waves, there is no problem. But what happens if you assume, like Einstein, that light is made of particles? And experiments have been done, and I will just show you here on this. Here what happens when you do the experiment with a light beam which is so faint that photons are produced one at a time. There is only one photon at a time in the interferometer, in the apparatus. You will see how this interference build up, you see that points, the photons arrive discretely on the screen, so they tell us, I am a particle, and at the same time, when enough particles have reached the spot, you get a fringe pattern. So collectively, the photons tell us we are a wave. So this seems simple when you look at that, but there is a terrible mystery here, because how can a single photon, which is alone in the apparatus, know that it cannot come on a dark fringe? For that, it has to know that the two holes are open. And so this simple experiment shows that there is no trajectory for a photon, and there is no trajectory for a particle, quantum particle either. The particle has to be through the two holes at the same time. This is called the superposition principle of quantum physics, which is displayed by this very simple experiment. There is another mystery here. Can you decide where the first photon will come? In classical physics, if you know the initial condition, you should be able to do that. In quantum physics, it's not possible. In fact, the initial photon and any photon can come anywhere, and it's a random process. And Einstein said in quantum physics, God is playing dice, and he did not like that idea at all, because he had remained at heart a classical physicist. And this is one point in quantum physics that Einstein did not like, but this is the way nature behaves. And then De Broglie came out about 10 years later, and he said, okay, if light, which is assumed to be a wave, is a particle, why not the opposite? Why not particles like atoms, electrons, which are supposed to be point-like? Do they have also a wave character? And he assumed that it was the case, and he used the same formula as Einstein and found that you have to associate a wave to each particle, the wavelengths being inversely proportional to the mass of the particle. So if you take a heavy object, the mass is so big that the wavelength is infinitely small, and you don't see the wave aspects. That's why we are not waves. We are well localized. But if you look at very small object, m very small at the atomic or electron size, then lambda can become large, and you have wave-like characters. And the same kind of interferences have been observed with electrons, and now they're observed with atoms and with molecules. And I just want to make a remark that De Broglie was a student of Langevin, and when he made this hypothesis, Langevin did not know what to make out of it, and he sent the thesis to Einstein. It was a year after the photograph I showed you before, and Einstein answered to Langevin, I think you can have it submit his thesis because he has lifted a part of the great veil which makes the microscopic world invisible to our eyes. And so you see, quantum physics is based on this wave-particle duality. And this is, again, blue sky research. It was done only to understand an effect which had no application at all. Light is an ensemble of photons and a wave, and atoms are particle and matter waves at the same time. What sense can you make of that? I will show you here something which may give you an idea. How do you read this sentence? You read it, light is a wave or light is a particle. This is an ambigram which was drawn by Douglas Hofstadter, who likes to make these kind of games. And you see, this depends upon your state of mind. For some of you, the neurons in your brain fire to say light is a wave, for others light is a particle. So it's the state of your neurons which decide. In physics, it's not the state of the observer neurons, which has nothing to do with that. It's the state of the experimental apparatus you are using. Because when you do an experiment with quantum particles, the system that you are using, the observer, the measuring device reacts back, feeds back into the system and changes its state. And what happens is which aspect is observed depends upon the experimental setup you are using. And this is what Bohr described as a complementarity principle. The wave and the particle aspects are complementary from each other, and which one is observed. If you can see the trajectory in the interferometer, you won't see the interference fringes because you will perturb the system in such a way that the fringes will disappear. And if you can see the fringes, you will not be able to tell through which side the particle went. This sounds strange for a classical physicist, and Bohr said, and I have to tell you the sentence because you cannot read it, if you are not shocked by quantum physics, it means that you have not understood it. So that's a kind of paradox. Bohr used to like this kind of statement, and it infuriated Einstein when they discussed together, because Einstein didn't like at all this kind of jokes about nature. And then a few years later, Schrödinger came out with the equation, which explains how this famous de Broglie wave evolves in space-time. So it's the equation which puts this theory in quantitative terms. I don't want to explain what it means, but you see it means that the way this wave evolves in time depends upon this quantity h, which is called the Hamiltonian, and which depends upon the forces acting on the particle. So if you know what kind of field force the particles see, you can see how you can find out how it evolves. And by solving this equation, you understand everything about atomic physics and about molecules and about chemistry. And to quote Dirac, Dirac said, you don't need to do chemistry anymore. You just have to solve Schrödinger's equation. If you have enough computer power, chemistry is finished. It infuriates chemists because, of course, it's not true. This equation cannot be solved if you have more than 2 particles. Even with a helium plus ion, which has only 3 particles, you cannot solve exactly Schrödinger's equation. But the equation is exact. To come back to Dirac, this equation has to be modified to take into account relativity. This equation was not relativistic, and Dirac wrote the equation for an electron whose velocity is not negligible compared to the velocity of light. And again, I don't want to make you understand what it really means, but I just want to show you that the equation is quite simple. It has Greek letters, which is more beautiful than Latin letters, and it has also a kind of symmetry with circular rotation of indices, and this is what Dirac called a beautiful equation. And Dirac had a very strong feeling that for a theory to be right, it had to be beautiful in the sense of mathematical simplicity. And this is the kind of equation that he obtained. And by looking at the solution of this equation, he found out that there were solutions which predicted the existence of a particle which had the same mass but the opposite charge, called the positron. So he discovered through the theory the existence of the positron. And each particle has its antiparticle. The electron has a positron, the proton has the antiproton, and you can build an antimatter with particles which have opposite signs. And cosmologists tell us that at the origin of the universe, there was a symmetry between matter and antimatter, and this symmetry was at some point broken, and all antimatter had disappeared. You find this antimatter only in reaction occurring in accelerators. And when an electron meets a positron, it annihilates with a release of energy in the form of gamma ray photons. So you see again the beauty of theory. You start from just trying to conciliate quantum physics with relativity. You get an equation, and this equation opens a new world with new particles that you had not anticipated. And this is what theory is about. And I think one of the big questions about blue sky research in this field is a very mysterious one for some people. How is it possible to explain that the physical world can be expressed by equations? How can you explain that mathematics, which were invented by the human mind, explain the world? And one part of the explanation is that mathematics expresses symmetries, and the physical world is full of symmetries. So if you take the symmetries that I described before, you get the relativity equation. If you take this kind of symmetry with quantum mechanics, you get the symmetry between matter and antimatter and so on. And these symmetries exist for physics. They don't exist in biology, because biology relies on history, on evolution, and you don't have this kind of time invariance and spatial invariance symmetry. We are not sure that the same kind of life exists in other planets, because there is the serendipity of evolution, and so biology has no equation. So I don't know whether it's better or worse. It makes the biological world much more open to all kinds of explorations, but physics has a symmetry, the beauty of this kind of symmetry. So I will summarize the strangeness of quantum physics. We have the strangeness of relativity that I already discussed, the fact that clocks evolve at different times, that you have a bent space-time. But quantum physics is even more strange. You have the superposition principle. A particle can be at different points at the same time. And you have entanglement. And entanglement is a concept which I will not have time to explain too deeply, but I just consider two particles. Each particle can have two different states, which I have shown in red and in blue. And they can fly away from each other at very large distances. And the particle is in superposition. Each particle is in a superposition of red and blue, which means that if you measure the particle on the left, with 50% chance you will find red, and with 50% chance blue. But as soon as you have found that for the first particle, the other one will give the same result. So it is as if you are casting dice, which can be very far from each other. They fall randomly, but it is the same randomness at two different points in space. This kind of randomness could be explained by classical rows. The fact that if you assume that you have some hidden variables which were random when you created the pair and they are propagating in space. But it's possible through very subtle experiment to show that this is not the case, that the state of the particle is not revealed, known before and revealed by the measurement. The state of the particle is created by the measurement. It didn't have any existence before, and it is a true randomness which occurs at the same time at two different points in space. This is maybe the strangest aspect of quantum physics. It's non-locality, which has been verified by a lot of experiments, and Einstein hated that. And this is a point which Einstein pinpointed to say that quantum physics could not be right. But experiments which have been done after his death have proven that it's the way nature behaves. So there is an entanglement. When you touch one particle, the other one is quivering as if you had some instantaneous action at a distance. But this is very subtle because you cannot propagate information in this way. You have random results at left and at right, and of course randomness has no information at all. If you want to convey information, you have to use this randomness combined with some kind of propagation of information through a classical channel, and this is called quantum cryptography. You can use this to propagate information and make sure that nobody can listen to your channel, but this cannot go faster than light. So quantum physics is strange, but does not violate a fundamental law of physics. You remember about 3 or 4 years ago, some people claimed that neutrinos were going faster than light. This would have been a terrible thing, because this would have collapsed all what we know about relativity and so on, and so all physicists knew that there was a problem and a mistake in the experiment, which was discovered later on. And the superposition principle and the entanglement have been illustrated by Schrödinger in the famous Schrödinger cat tail. You know, Schrödinger assumes that you have in a box a cat which is here, and here a single atom, which can be prepared in a superposition of being excited and de-excited. And for single atoms, we know how to do that. If the atom is excited, nothing happens to the cat. If the atom is de-excited, it means that it has emitted a particle which can trigger a device which will kill the cat. Now, the atom and the cat are separated by some distance, but they are entangled by this process. And this entanglement is very strange. It means that the cat and the atom are in a superposition. For the atom, we don't care because nobody has seen directly an atom, but we all see cats, and we don't like this idea, and Schrödinger did not like it either. And we are doing now in the lab some small version of this cat system, and I will conclude my talk by saying a few words about that. So what I want to say in the last part of the talk is to connect this blue sky research to innovation and applications. You know, we are in a period where if you tell to agencies that you want to do blue sky research, as you said, you won't get money. So you have to pretend at least that there will be an application. And there are good examples for that, as I will show you now. But what I want to say is that the road from blue sky research to innovation is often a very serendipitous one. So if the guy working in the agency tells you, okay, tell me, I will found your blue sky research if it has application. What is the percentage of blue sky research which will give rise to application? And my answer is that it's a very small one, 5%, maybe 10%, maybe 1%. But the other part of the answer is that we don't know which one it is. So if you don't find everything, you might miss really the important point. And I will give you some example of that coming from the field of research I'm doing, which is atomic physics. The story started in the 1920s, the same year, 1922, when Einstein visited Collège de France. One of his colleagues, which Einstein knew very well, Otto Stern, was working in Hamburg on atomic beams. He was heating in an oven silver atoms. The atoms were effusing in vacuum from the oven in straight line, and he was applying gradients of magnetic fields to find out whether these atoms were carrying magnets. If the atom was carrying a magnet, the magnet would be deflected in the field. And so he was looking at that. And to his big surprise, he found that, in fact, the trajectories after the magnet were quantized. The particles came to 2 spots only, which he recognized by observing that the magnet, each atom was carrying, in fact, the electron of the atom was carrying a small magnet, and the magnet could take only 2 directions, up or down, in the magnetic field, giving rise to 2 spots. And you see here the first signal observed here. You see here the 2 spots, and of course, if you go out of the magnetic field, the two spots coalesce. And so this signal here, this very simple trace, which is just observed on a photographic plate, is really announces, heralds a huge amount of modern technologies just from this very simple experiment. So this apparatus which separates spin up and spin down. A few years later, a young postdoc came to visit Otto Stern. It was Isidor Rabi, and he was fascinated by this experiment, and he decided to reproduce it at Columbia University when he came back. And he was looking not so much at the spin of the electron, at the magnetic moment of the electron, but he was trying to find out whether the nucleus of the atom also carried the magnetic moment. And for that, he used an atomic beam. And I just give you the principle of the experiment here. Again, you have a furnace, and you have a gradient of field taking opposite direction in part A and B. So if you have a magnetic moment in one direction, the particle will be deflected like that, and with the other gradient like that. So it would have a S-shaped trajectory and be detected here. Now, if something happens here in zone C to change the direction of the magnetic moment, the particle will miss the detector. And what Rabi did here was to apply a radio frequency field, a field which had the right frequency to flip the magnetic moment from the upper to the lower state. Each magnetic moment orientation is an energy level, and the distance between this energy level corresponds, according to Planck's law, to a radio frequency. And so he was able to observe this kind of resonance when he tuned the frequency of the field here. This was called magnetic resonance, and by that experiment he studied the magnetic moments of a lot of atoms inside molecules, so it's called the molecular beam technique. And this started a school which had huge ramifications and gave rise to a lot of interesting results. I show you here a headline which was in the New York Post in 1939. There was a conference to which Rabi attended, and some journalists were interested with what Rabi said. Rabi said, "We are all radio stations, all atoms in humans found to emit and receive long waves." And here you have the statement, "Everything on Earth is a radio broadcasting and receiving set, unconsciously sending out and receiving long-wave wireless messages." And this is the announcement of magnetic resonance imaging, of nuclear magnetic resonance, and so on. In our bodies, in any piece of material, the spins, the magnetic moments are rotating in magnetic fields, and if you can detect this rotation, you can do fantastic things. In the time of Rabi, it was not possible to detect because the only way to detect was to detect the atom. And of course, the atoms in your body, you cannot detect them. But as soon as you can pick up the radiation, then you are in business. And to pick up the radiation, you had to wage the war because radio wave detectors were developed for radar applications during the war. And 2 young physicists, Felix Bloch and Ed Purcell, developed the magnetic resonance method. Now, the atoms are in a bulk material here, solid or liquid. You have here a frequency generator which emits radio waves through this loop. It makes the spins rotate here, and you pick up this rotation with this antenna. And as you change the frequency generator, you see resonances which are a signature of the elements that you have in the medium. And they also noticed very quickly that these lines are very sensitive to the perturbation that you have in the environment of a molecule. You have shifts due to small fields which are produced by neighbor molecules, and so you can use this signal as a probe of what happens inside the material. I like to show the next picture here, which is a part of Purcell Nobel lecture. He got the Nobel Prize in 1952, and I like this sentence because it tells a lot about blue sky research. I remember in the winter of our first experiments, just 7 years ago, looking at snow with new eyes. There the snow lay around my doorstep, great heaps of protons quietly processing in the Earth's magnetic field. To see the world for a moment as something rich and strange is a private reward of many a discovery. So Purcell had a kind of poetic mind, and in fact he understood from there that you can use this rotation, this invisible phenomena to do new things. And of course you know that the end result was magnetic resonance imaging. We have protons in our body which are in water molecules, and these protons, hydrogen protons, rotate. They rotate faster and faster in high fields, so you have to put the bodies in a huge magnetic field to have rotation at high frequencies. And if you are in an inhomogeneous magnetic field, the frequency will depend on position, and if you have powerful computers, you can reconstruct the density of protons inside your body, and this gives these 3D images which are really amazing. And you can even do better than that. You can make functional magnetic resonance imaging, use the fact that if you think about something, you activate some part of your brain, so the blood flux increases. It carries hemoglobin, which has magnetic moments. It changes the magnetic environment of this part of the brain, and it changes the signals. And from these changes, you can find the part of the brain which are flashing when you think. And now there are experiments which use this kind of magnetic resonance imaging to observe the phenomena of consciousness. When you become conscious of something, you have a lot of parts of your brain which flash simultaneously. You have waves which you can detect through magnetic resonance imaging. So you see really that this is a fantastic application. But it was not all. A student of Rabbi Ramsey made a small change in the molecular beam apparatus. Instead of having one zone in which you apply the radio wave, it had two separated zones. And in this way, they were able to observe, through the Stern method, not only a single line, but fringes. The probability for the atom to flip as a function of the frequency of the field took this shape with very narrow fringes. And it was possible to feed back the frequency of the source to stay on the center of this fringe. And by this reaction mechanism, it was possible to lock the frequency of the radio wave to the exact frequency of the atom. And quantum physics tells us that all atoms in the universe of a given species oscillate at the same frequency. So this gives an absolute time measuring device. This is called the atomic clock. And this is, here you don't know what it means. You have a precision of 1 second over billions of days, just with standard clocks. Standard clocks do not deviate from one another by more than 1 nanosecond per day. So what is the application of that? You send these clocks on satellites, you synchronize the clocks with each other, and then they send signals to the detectors that you can buy for a couple of $100. And by triangulation, you get your position on Earth with a precision of about 1 meter. In 3 nanoseconds, the light is going 1 meter. And for that, you need to do relativistic correction, because all these clocks are speeding with respect to you. So you have special relativity, and they are in a different gravitational field. You have general relativity. If you do not make the corrections of relativity, you will be off by kilometers. So you see that the small apparatus that you are using, without thinking about it, uses quantum physics, special and general relativity for a very, very practical application. The last one is a maser. Again, an atomic beam. Again, people who are working at Columbia, Charlie Towns, who made a device in which the ammonia molecule was put in the upper state of a transition which was resonant with a cavity, and he was able to amplify the field in the cavity, and he built the first maser, acronym for microwave amplifier by stimulated emission of radiation. The stimulated emission process was discovered by Einstein in one of his papers of 1916, and again, it's an application of blue sky research. The first thing operated in the microwave domain, but then it was extended in the optical domain, and it becomes a laser light amplifier by stimulated emission of radiation. And this is, of course, a story that we all know about. The laser had a lot of applications in all fields of technology. So I will conclude now by some personal remarks, because when the laser came out, was invented, I was lucky to start my own research in the lab, in a lab which was at École Normale Supérieure, as I was a student there. So I can give you the explanation. Normal means it's a normal school. It's a school which was supposed to form teachers for schools during the French Revolution. But it was the highest school of this kind because it was to form teachers of teachers, professors at universities and so on. So it was called the École Normale Supérieure. We have now a president who says, I am a normal man. So it's a different meaning of the word normal. So this was the early days of the laser, and this picture was taken on the day Kastler got his Nobel Prize in 1966. So Kastler got a Nobel Prize for optical pumping. Optical pumping is a variant of NMR, but it's an NMR in gases. You use radio frequencies to orient at will and to manipulate the magnetic moments of atoms. Then a few years later, Claude Cohen-Tanuji was a student of Kastler. In 1997, got a Nobel Prize for manipulating atoms, not with radio frequencies, but with laser light to cool and trap the atoms. And Claude Cohen-Tanuji was my thesis advisor, and you might not believe it, but here I am. And what we did was to extend these techniques, but at the level where the sensitivity is such that we can do kind of NMR experiment with single photons and single atoms. And so this is the topic of cavity quantum electrodynamics. We trap photons between highly reflecting mirrors, and we send atoms one by one through this cavity. And these are special atoms, very excited Rydberg atoms, which are prepared with lasers. And we extract information from these atoms to find out what is the state of the field without destroying the photons. And in fact, in these experiments, we entangled photons to the atom crossing the cavity. So I don't want to describe the experiment. I just want to make the connection with what Dave Weinland had been doing in Boulder. You see, what we do in Paris is to trap photons and use atomic beams to manipulate the photon and detect them. And in Boulder, Dave does the opposite. He traps atoms with electrodes and use laser beams to manipulate and detect the atoms. So what we are doing are, so to speak, the two sides of the same coin, manipulating non-destructively single photon with atoms or single atoms with photons. And the important point is non-destructively. And for photons, it's not easy. You know that most of the time when you detect photons, you destroy them by the photoelectric effect. Here, the interaction is very subtle, and we extract information from the photons without absorbing them. And you see here, for example, a picture showing 5, 3, 2, and 1 atom in a Boulder ion trap. And here you see photons escaping one by one from our cavity. So you see in both cases you can count atoms or photons like you would count marbles in a box. So this kind of experiment illustrates the particle aspect of light. You see when photons escape from a box, they don't escape through an exponential law. If you follow what happens, you have a staircase because the photons go out one by one. To recover the exponential law, you have to do it over and over and over and average over a large number of results. But the last thing I would like to do is to come back to this dual aspect, and I want to describe an experiment in which we explore the wave aspect of the photons, and this allowed us to prepare Schrödinger cats, and I just want to say it with 1 or 2 slides. What is a field which has a well-defined phase, a coherent field of light? So something that every engineer knows. A field which has a well-defined phase, just a sine wave, which has an amplitude, which is very which is this thing, but it has also a phase which defines the time at which the crest of the wave passes through a maximum. And you see here, for instance, 3 fields which have the same amplitude but which are out of phase with respect to each other. And engineers like to represent that by vectors in a plane. It's called the Fresnel plane. The length of the vector gives the field amplitude, and the direction of the vector is related to the phase. For instance, the 3 fields are 120 degrees out of phase with respect to each other. What is the quantum picture of that? The quantum picture is about the same, except for the fact that the tip of the vector now is fuzzy, because you cannot define with infinite precision the amplitude and the phase. They are related by quantum uncertainty, and if you define well the phase, the amplitude, you will lose the phase. So you have a compromise, and the tip of the vector is within an uncertainty circle. And this circle defines a Gaussian function, and so a coherent field in quantum physics is represented by a Gaussian distribution in phase space, which I have shown here in false colors. So what happens now if you have such a field in a cavity and you send a single atom across the cavity, and you prepare the atom in a superposition of 2 quantum states, E and G. So the atom goes here, a pulse of microwave, prepare it in a superposition state, and then it crosses the cavity. And each state will act as a small refractive index, which will shift the phase of the field, but in opposite direction, depending upon whether the atom is in one state or in the other. So when the atom leaves the cavity, you have now a Schrödinger cat. You have a field which has one phase and the other phase at the same time correlated to the state of the atom. And it's entanglement because the field is here and the atom is there, and they are entangled with each other. And if you want to observe that, you can play a last trick. Before detecting, you send the atom through a second microwave zone, which mixes the levels again. And if you do that, when you detect the atom, you can no longer know what was the state of the atom when it crossed the cavity because you have mixed them again before detection. And according to quantum physics, this maintains the ambiguity of the field, and the field is projected into a cat state superposition. Then we send other atoms, and we use this atom to detect the state of the field, and we get the Wigner function. We get a kind of map of the field, and you see you have 2 peaks. This is the live cat, and this is a dead cat. And you have fringes in between. So I don't know what the fringes would mean for a real cat, but here the fringes are here. You have interference between the live and dead cat. And you can do even more. You can take pictures of this as time goes on, and you can make a movie. And I will show you the movie now. And you see that after a few milliseconds, the fringes are washed out. So this is decoherence. This explains that after a very short time, the coherence between the live and the dead cat is destroyed, and you get 2 peaks. The cat is either dead or alive, but since you make averages over a large number of realizations, 50% of the time you get a dead cat, 50% of the time a live cat, and this wave function gives the 2 peaks. So, and this is in complete agreement with the theory of decoherence, which was which was expressed by Dirac. This paper is a very interesting one. This is a paper which triggered our interest in this problem. And we found that the decoherence rate increases with the cat size. If you make more and more photons, the time it takes for the fringes to disappear becomes shorter and shorter. And it explains why you cannot do that with a real cat. Because the decoherence time is inversely proportional to the number of quanta you have in the cat. So how many quanta do you have in a cat? Let's say 10 to the 25 molecules. So you have to divide the lifetime of the cat by this number of quanta. So you take 10 years, 15 years, you divide by 10 to the 25, you find a picosecond. And I challenge anyone to kill a cat in less than a picosecond. So in fact, you cannot. This means that with large systems, you cannot prepare the state superposition before they have lost their coherence. And this gives you a glimpse at the quantum to classical boundary. So why is it important to be able to do that? The first question is just curiosity. Is it possible? How does nature behave at this level? The answer was not that obvious. Schrödinger said, we never experiment with single electrons, atoms, or small molecules. In thought experiments, we assume that we do, and it always results in ridiculous consequences. So you see that, and it's strange because it was 1952, and at that time, single particles were already detected in accelerators. But what Schrödinger thought is that you cannot detect them without killing them. You detect the result of collisions. And he said this is like post-mortem physics. In fact, high-energy physicists are like paleontologists. They observe traces of events which have disappeared. Here we are doing in vivo physics with cats which are at the same time dead and alive. Another explanation is that all systems react faster and pack more information per unit. Small systems react faster and pack more information per unit volume. So if you want to get more powerful devices, you have to get to smaller and smaller systems. And this is Moore's law. But we are now reaching to a point where we code information into single atoms. So we have to know how single atoms behave. And it's not only a quantitative fact, it's also qualitative, because you can make superposition of states. And quantum physics makes a wide range of new states, superposition of states accessible for quantum information processing. And we all know that people are trying to look at more powerful computers or simulators. This is quantum logic. You can have more secret communication by exchanging pairs of entangled photons. This is quantum cryptography. And you can perform more precise measurement. And again, I advertise for Dave Weinand's work. He has a clock which works with a single ion, which is so precise that two clocks of this kind do not deviate from each other than more than 5 or 6 seconds during the age of the universe. And he had just moved one clock up in the gravitational field of the Earth, and he has seen about 5 years ago a difference in the rate of the clocks when the difference in altitude is 30 centimeters. Since then, better things have been done. Now the resolution is about 1 centimeter. So it means that what time means is not clear, because it depends. You have to know exactly what is the gravitational field if you want to measure the time with that kind of precision. But it might have applications. For instance, if you move the clock on the ground, you will be able to see if the gravitational field is modified by minerals or by small motion of the ground. And Japanese are very interested in trying to use that for detecting precursors of earthquakes, for instance. And this explains why this kind of clocks, Japanese are very good at developing this kind of ultra-precise atomic clocks. So will a Schrödinger cat state become a powerful computer? So we try to exploit superposition and entanglement. And of course, the big challenge is decoherence. And nobody knows whether this will be possible. I have my doubts about that. And I just want to say that extrapolating today's physics to predict future innovation is a very risky business. And just to show you an example, I come back to 1900. Lord Kelvin did not believe in all of this physics. And 1900 was also the time of the World Fair in Paris, where there was this feeling that the progress was going to become universal, and wonderful things would come out, and postcards were edited everywhere in Europe, and this is the kind of thing which were predicted. You will be able to dictate to a machine directly. You will have transportation with balloons, and you will have hybrids between train and ships. And you see, this is not very impressive, and nobody had predicted MRI or the GPS or the computer or the internet. So I don't want to make predictions. Niels Bohr said it is hard to make predictions, especially about the future. Think about this prediction if you ask what will happen in 2100. But one thing is sure, without basic research, without blue sky research, novel technologies cannot be invented. The past teaches us that wonderful applications always emerge in a serendipitous way from blue sky research. And so this will be my last slide, and I hope everything will show up here. Novel technologies often come from in unexpected ways from blue sky research. And blue sky research needs two priceless ingredients. I say priceless because, of course, there is money, but money is not priceless. So what are the priceless ingredients? It's time and trust. You need a lot of time to do this, and you cannot realize this kind of experiment on short-term contracts. You cannot be asked what will be your timetable, what will be your milestones in a year or 2 years from now. So you need to work in an environment where people trust you and give you some regular funding to work at your own pace. And research is fully successful where these two ingredients are present. It was a case at École Normale Supérieure. It was a case in Dave Weinand's lab too. He worked for 30 years to develop this kind of devices. And it is not really favored by the laws of the global market, which emphasizes, instead of time and trust, speed and fast results and contracts. And contracts is the opposite of trust. It means that you get money if you promise that you will do things. Of course, you can bypass that. We promise things that we won't do, and the people who give you the money know that you will not do it. But it's a loss of time. It's a lot of, you have to make a lot of paperwork, and I am very, very upset by the fact that this is asked from young people. Young people have not been trained to do that. They have been trained to do physics, and they have to become entrepreneurs to get their money, and this is just a loss of time and a big problem. So I just want to conclude by acknowledging my co-workers. Nothing of what I have done would have been possible without Jean-Michel Raymond and Michel Boyne, who had been my students, and I was lucky to keep them in my group, and we have been working for all these years. And I think there is some kind of unfairness in the Nobel Prize, that you pick up the leader of the group and the others are left behind. But of course, I am very lucky because I understood the rule of the game, and the atmosphere in the group has not been spoiled by, I must tell you, by the Nobel Prize. And so we are still working together, and this is the group with young people, students and postdocs. And with that, I apologize for having much longer than what is expected from me, but I thank you for your attention.
Thank you, Professor Roche. There was a fantastic review of modern physics, from the birth of quantum mechanics, the development of general relativity, to your own groundbreaking work. The beauty of fundamental physics, the mystery, but also the analog to modern technologies like MRI that were developed out of the realization that something was there. We're running a bit behind, but it was a fantastic talk, so I think that's no problem at all. I forgot in the enthusiasm of opening the evening to introduce myself. My name is Sven Rogge, and I'm the head of school for the School of Physics. And it's extremely exciting to live in a world where we can actually work with single atoms and look how quickly they decohere or not decohere. This is an amazing time. With that, I want to open the floor for questions from the audience.
So you need a course on quantum electrodynamics. I can. Feynman has written diagrams. You know, you have diagrams showing the propagation of electrons. They exchange photons, and the force is produced by the exchange of photons. And when you sum the diagrams, you find the trajectory that they repel each other through this force. But it's difficult for me to. First of all, I would have to rehearse my own quantum electrodynamics to give you the answer. But I can tell you this is within electrodynamics. And I want to say another thing connected to Dirac. The first glimpse to quantum electrodynamics, of course, was Dirac's work, in which he wrote the equation for the electron, found the electron hole ID giving rise to the positron, and he wrote the Dirac equation within an electromagnetic field, and found out he was the one who discovered the annihilation and creation operators for photons. And I heard from someone who knew Oppenheimer that when Oppenheimer was a postdoc, he went as a postdoc, I think it was in Heidelberg, and he met Dirac there. And Dirac had not published this paper on the photon interacting with the electron. And he gave the manuscript to Oppenheimer. And Oppenheimer read the manuscript, and he said to this friend that I met, that he told me the story 50 years later, that Oppenheimer was really, it was the most revealing moment of his scientific life. He could not sleep that night because he understood that Dirac had found out how Maxwell's equation could be quantized. It was not the end of it. It took another 20 years to make it really formal, but it was the first step in this direction. This was also a contribution of Dirac. So here again, this is a very deep question in cosmology, and I don't know anything about it. What I know is that in the universe that we know about, there is no evidence that antimatter seems to have disappeared. And I think from what my high energy physics friend tell me that it is one of the mysteries of cosmology. One does not understand why there has been this breaking of symmetry and all the antimatter has disappeared. But again, there was a joke or a story told by Feynman that if you meet an alien coming from another planet and you don't know whether it is in your universe or the other, don't shake hands with him, because if he's made of antimatter, it will be a disaster. It's a very deep question. You might think maybe that the brain has evolved in a way to understand mathematics, because the mathematics explains the world, and if we can explain the world, it gives us an evolutionary advantage. But I'm not sure at all it is the case, because what happened with mathematics is maybe 2,000 years old only, and this is much too short for evolution to occur at this scale. So I think this is a kind of afterthought which has nothing to do with reality. I think it's a mystery. I don't know. Maybe our brain is trained to see symmetries and to recognize symmetries, and recognizing symmetries is a part of mathematics. So maybe the connection is through that. Maybe we will learn about that more and more with the experiments that people are doing with functional NMR, because now we can look at the brain what happens to the brain when you make very simple calculations, adding or subtracting numbers, and so maybe one day we'll be able to follow through NMR imaging and other techniques what happens when we do mathematics, and maybe we will learn things. But it's a very fascinating aspect of neurosciences. I must say there were rumors in the last couple of years before the prize, but after we had done the result, I think maybe what helped in this case is again a symmetry. The fact that the experiment we are doing in Paris were the mirror image of what Dave was doing in Boulder. And this symmetry, we had recognized it long ago. About 20 years ago, we realized that some experimental signals we were obtaining in our lab looked very much alike the one that Dave was obtaining in his lab. And maybe this kind of symmetry pleased the Nobel Committee, and this explains why it was given in this way. But we enjoyed very much this kind of competition, and we enjoyed very much the fact it was ideal because we were not working with the same system, but there was an intellectual link. So it's the best kind of competition because what we were doing was different, but still we could discuss and cross-fertilize our thoughts by talking to each other. And I just wanted to add that for the last 20 years, we have been very good friends, Dave Wineland and me, and not only us, but our family and Claudine and Sedna Wineland are friends also, and it took us some time to get the Winelands used to take vacation, because in the United States it's not the case, so Claudine was able to convince Sedna to convince Dave to take vacation, and the first vacation we took was in Italy about 20 years ago. And at the end of after a few days, Dave became very nervous, and I realized it was not the right thing to keep him away from his lab, and so vacation ended, but not the friendship.
For nearly 200 years, the Royal Society of New South Wales has been drawing upon its rich heritage from the Royal Society of Edinburgh in encouraging studies in science, art, literature and philosophy. No better example of that heritage is the very deep and strong relationship that we have with the University of New South Wales, particularly with the science faculty. And I would particularly acknowledge Merlin Crossley and Les Field and Sven for the very strong relationship that we have. Indeed, we have one of our distinguished fellows and several of our fellows here tonight. So it's a matter of great pride for us to be associated with the presentation of the Dirac lecture. We'd like to thank you very much for that, and I'd like to add my thanks to Professor Hirosh for a very stimulating talk. Thank you.
Thanks, Professor Hiroshi, for the excellent lecture tonight. The Australian Institute of Physics also has close links to universities, industry and a number of other institutions. We have a number of events throughout the year. Just to mention at today's lecture, you are French, so I thought it would be quite pertinent to mention a famous French aviator. His name is Antoine de Yushi Pone, and he actually mentioned something which is quite interesting. It's very pertinent to tonight's talk. If you want to build a ship, don't drum up people to collect wood or assign them tasks, but teach them to long for the endless immensity of the sea. So this means the ship itself is only a means to discover the beauty and wonder of the sea. People's love of the sea will ensure a ship is built. Professor Hiroshi's fascinating lecture on scientific work in general gives us that same feeling, the beauty of nature explored through the tool of scientific research. So what I'd like people to go away tonight to think about is we shouldn't be saying to scientists, we shouldn't be saying to people, become a scientist because we need more scientists. What we should be saying is put yourself in a position, guided by the tools of science, to go on a fascinating journey of endless surprise and discovery, especially blue sky research. Thank you very much.
Nature and about the place of mind in the universe have first been addressed, of course, during the history by religion, by mythological stories, even by philosophy. But the question has been addressed by science only a few centuries ago, and one might say that the story started during the Renaissance, when objective observation of the world, followed by rational thinking, gave rise to modern science. And blue sky research is about this modern science. I think one way to start this talk would be for me to say to you a few words about the institution I belong to. I will not be talking about the École Normale Supérieure, but about the other one, the Collège de France. The Collège de France was founded, in fact, during the Renaissance in 1530 by the King Francis I, who had been waging long wars in Italy, but from Italy he brought back not the warrior spirit, but the spirit of the Renaissance. And when he, in 1530, he decided to found what was then called the Collège Royal. The idea was to gather scholars who were teaching, giving public lectures on all kinds of topics which were not taught in the medieval Sorbonne. The first topic was mathematics, and also languages spoken in the Middle East, like Hebrew and Arabic, which were not taught in the Sorbonne. And then things have expanded. All fields of knowledge have been taught in this Collège de France, which has survived all revolution upheavals, and which is now called the Collège Royal, became in the 19th century the Collège de France, and this is the building in which it is located today. There are about 50 professors who are specialized in all fields, in exact science and humanities as well. And I think the spirit is blue sky research in the sense that the research is free. They follow their line of research as they want. They just have to change their lectures every year. And this is, I think, blue sky research in the true sense of the word. A few luminaries in Collège de France have been Champollion, who deciphered the hieroglyphs in the 19th century. I know that the British think it's Thomas Young who did that, but the French says it's Champollion. And Ampère, who discovered the laws of electricity and the connection with magnetism. Claude Bernard, who was the first who started experimental medicine. And Henri Bergson was a philosopher. So you see, it spans a wide range of fields. And this knowledge, the important point, and I think you have it here also on at the bottom of this poster about New South Wales, mixes humanities and science. And it is very important, because if you want to do science, you have to have an open mind, and you have to have a mind who mapped the cosmological background, because it was carrying a lot of radio frequency detectors. And here you see these two buildings at right angle, kilometer-long buildings which house laser beams, which measure the distances between two mirrors on the two arms. The idea is that tiny changes in this mirror lens will allow us to detect gravitational waves coming from the collapse of stars, from explosion of supernovae, and so on. So this is really blue sky research in the true sense, because we are looking at the sky and trying to get information about what's going on. And you know, when you look at these huge realizations, which have involved thousands of workers and technicians and engineers, the scale reminds us of what happens during the Egyptian time. It's pharaonic in dimension. And in the Egyptian times, the pyramids and the temples were built in order to make sense of the place of man in the universe too, but it was through religion. Here it's through science, and we learn where we are in the universe through these kind of experiments. This started long ago with Copernicus and Galileo. We learned that the Earth was not at the center of the universe, and it was rotating around the sun. And in the 20th century, we learned that the sun is only a small, at the peripheral part of our galaxy, and that there are billions of other galaxies around. And this is what we learned from this kind of experiments. You see here a famous picture from the Eagle Nebula taken by the Hubble telescope, and it looks like clouds, and these are gigantic clouds which are light years in dimensions. Inside these clouds, stars are continuously forming, so we learn that the universe is not static, it's in perpetual evolution and formation. And we also learned something new during the last 20 years. Most stars, maybe all stars, have planets going around them, and these planets are now detected. Thousands of these planets have been detected. One way to detect them is just to look at the tiny change of the light of the star during a partial eclipse, when the planet is between the star and the observer. There's a very slight change in the luminosity of the star, which is very difficult to detect, but with the improvement in astronomical observation, it's possible to do that. And some of these planets are within the distance range which makes them inhabitable. So very probably we learn soon that there is life in other parts of the universe, maybe intelligent life. But this is blue sky research because we will never be able to get there. These are at millions of light years or thousands of light years, and physics tell us that it's impossible to get there. So does it mean that it's not important to know? It's certainly important to know because it gives us a feeling, it tells us our place in the open to free thinking, and this is something that you get from humanities. And in order to show the connection with that, I will start talking about blue sky research and how it probes the universe and the place of man in it. That is, science for the universe and the place of man is humanities. And I show here two different pictures. On the left, you see a clay tablet on which strange signs have been written by a scrivener about 4,000 years ago. And for the common man, it makes no sense. For the layman, you cannot make any sense of it. And on the right, you see in false colors the intensity fluctuations of the cosmological background of the universe, which has been detected by satellites orbiting the Earth. And again, for the layman, it makes no sense. Now, the research means that you take information which makes no sense unless you have a theory or unless you have a model, and from your knowledge, you can make sense out of it. You can relate it to a context and build theories or build models which teach you think beyond the mere aspect of these things. For example, in the left, a specialist in Assyriology will be able to tell you whether this message is a contract or a list of furnitures for the king's army or something like that. And from thousands of tablets of this kind, a civilization which lived 4,000 years ago revives, and you learn about it. And on the right, from these fluctuations, cosmologists will tell you that it tells you what happened 14 billion years ago when the universe was very young. These fluctuations, which are of quantum origin, gave rise to the start of the stars and the galaxies, and you understand what happens in the universe. So you see, it might sound a little bit artificial, but you see that blue sky research is in all fields, and it means that you have first to collect data, but collecting data is not enough. You have to make sense of the data you collect. You know that Lord Kelvin said at the beginning of the 20th century that beyond physics, it's only collecting stamps. And by that, it means that collecting data and just making collections is not science. To do science, you have to connect the data that you have obtained through a theory and in order to predict new things. And this is what blue sky research is about. And a lot of money is spent on blue sky research. I will give you here a few examples. These are telescopes on top of an Hawaiian mountain which are probing the depths of the universe. Here you see one of the detectors at CERN, a huge cavern underground, which detect the results of collisions between particles, and which was used, for instance, to discover the Higgs boson 2 years ago. Here you see the Planck satellite before it was launched, and this satellite is one of the satellites of the universe, and we learned that our place becomes smaller and smaller and smaller, and paradoxically, we become greater and greater and greater from this knowledge because we know more and more about the world around us. So this is the first part of the first aspect of blue sky research I wanted to talk about. Now, it's difficult as a physicist to talk about blue sky research without talking about theory and the connection between theory and experiments. All the great physicists which have succeeded one another since the 17th century, Galileo, Newton, Maxwell, Einstein, Schrödinger, have given, or Dirac, have discovered an equation which describes some part of the natural world. And this equation describes in mathematical terms the beauty of the world because it describes some kind of symmetry in the world around us. And this gives a lot of predictive power and beauty to the theoretical equation. Of course, it's very hard to give a feeling about the aesthetics of an equation to someone who is not a mathematician, but I'll try at least to give a feeling about that. And the first equation I will start with is, of course, the only one that everybody knows. It's the most famous equation, and you see, with only 5 symbols, it describes a lot of things. It tells us that any speck of matter, however small it is, contains energy, and energy is related to the mass. And because the speed of light is so big, you have a huge amount of energy within matter. And if during a reaction, chemical reaction or nuclear reaction, the final states have a different mass than the initial states, the mass difference is transformed into energy. If this energy is released quickly, you get the atomic bomb, or more precisely, the nuclear bomb. But if it is released in a continuous way, you get nuclear power plants, or you get the energy released by the stars. It's transformed into light, and the light transports the energy to the Earth, and this is how we can live here. Until the 20th century, this was a mystery. Nobody knew how long the stars will be able to radiate, because nobody knew what was the origin of this radiation. But as always in physics, or very often in physics, when we look at an equation, you ask other questions, and it starts to become complicated, or more complicated. For instance, I told that light has energy, carries the energy from the sun to the Earth, but we also know that light has no mass. So how come you can have energy without mass if you have E equal mc squared? And the explanation comes from the fact that the real equation is a little bit more complicated. In fact, what I wrote, the equation I wrote was the equation relating to a motionless object, and m was the rest mass. Now, if the object is moving, you have a more complicated relation involving the mass, the energy, and the momentum of the object, the momentum being classically the mass.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.
Thank you very much for this very kind introduction, even with citations in French. I am deeply honored to have been invited to give this Dirac lecture and to receive the Dirac medal. You know, Paul Dirac was, since I started learning quantum physics a long time ago, he was one of my scientific heroes. His theoretical work is extraordinarily deep, and it is motivated by pure curiosity. So it's a perfect example of blue sky research, the kind of research I would like to talk about to you today. In fact, with some other great scientists, people like Einstein, Bohr, Schrödinger, Heisenberg, De Broglie, whom I will be talking about too, he changed our view of the world, not only at the microscopic scale, but also at the macroscopic scale of the whole universe, because quantum physics and relativity are important to understand the world. And this understanding of the world is motivated only by curiosity. There is no reason when they started this research, they were not looking for some utilitarian application, and this is what blue sky research is about. So I will be talking to you about the beauty of blue sky research. I hope I will give you a feeling about it, about its necessity too, and you mentioned the fact that it becomes difficult to get funding for this kind of research. And I think one of the reasons the funding should come is that in spite of the fact that it is not aimed at specific application, very often in serendipitous ways, blue sky research has led to innovations which have changed our lives, and I will talk about that a little bit today. Of course, the search for understanding nature and man has started a long time ago. Questions about nature